Hello and welcome to the course on C Programming Learn to Code series. This is the 31st lecture of Unit 2, and in this lecture we will continue our discussion on operators in C. Today we will discuss about bitwise operator. So let's begin. C programming language provides 6 types of bitwise operator, and the names are bitwise AND, bitwise OR, bitwise XOR, ones complement, left shift and right shift. The corresponding symbols that are used for bitwise AND is ampersandage. For bitwise OR is called this particular symbol is called actually the pipe operator or pipe symbol. Okay, so we are using a pipe symbol to represent your bitwise OR. Then this symbol is called a caret symbol, which will be used for your bitwise XOR, and for ones complement we are using a tilde symbol, and for left shift you can use less than symbol 2 times, and for right shift you are using greater than symbol 2 times. Okay, so these are the symbol exactly used for representing your bitwise operators, right? So what exactly bitwise operator means? So bitwise operator means, so these operators are applied to the values in bits. For an example, we know that every number is getting represented with the help of binary numbers, and every binary number is generally called a bit. So whenever we perform any operation on these binary numbers, then we will use these operators. Okay, so that's why bitwise operator are separate, means it is a different concept than the regular operators. Okay, so let's begin. You can see here all these operators are binary operator except this ones complement operator. So let's begin the discussion of all these operators. But for this lecture I will concentrate on the AND operation only, bitwise and other operator like your bitwise OR and bitwise XOR is purely based upon this AND operator. If you are able to understand the AND operator properly, then also you can able to write means you can solve any problem that is related to your bitwise OR and XOR. And other operator, regarding other operator I will take another class for that. So let us start with the truth table of all these bitwise AND, OR and XOR, which is something like this. We know we have already taught, I have already taught you all these truth table regarding your AND operation, OR operation in your logical operator class. But let us discuss over here again. In bitwise AND, what will happen if both the inputs are 1, then only the output becomes 1. Okay, so this is OR operator. Actually this should not be used, the symbol should not be this, the symbol should be A or B. That is your pipe operator we have to use. Well, so you can see here whenever the inputs are, both the inputs are 0, then only you will get the output to 0, otherwise you will get 1. Okay, similarly for XOR operator, if both the inputs are similar like 0 0 and 1 1, you will get the output as 0. Okay, and in other cases when the inputs are dissimilar to each other, then you can get the output as 1. Fine, so this is the truth table. You have to remember this truth table properly, and how to remember this truth table I have already discussed in the logical operation, logical operator discussion. So we know I know that you will be able to remember all these truth tables. So let us first understand about the let us discuss about all the detail of this AND operation. We will take some examples and we will try to solve this AND operator properly. So if you are able to understand this AND operator properly, then you can solve other problems that is related to OR and XOR too. Okay, so let's begin. So here I am taking one example, which is a C program over here. So the 3 line I have written inside this program. We know that this part, that is your has include stdio.h, int main and return 0. These are the structure of the C program, so I will not explain anything about this. So let us concentrate on this 3 line only. So what are the 3 lines? That is int x. So what will happen whenever we are declaring int x? Then automatically a variable named as x, okay, will be the memory for that variable will be allocated and the name will be x. Then what we have written? We have written x is equal to 12 ampersand 23. I would like to remind you one thing over here. So if you remember, we have talked about your AND operations and logical operator. So we are using double ampersand for representing this AND operation. So if you do the same thing, suppose x is equal to 12 double and 23. So this is a logical operator. So what value will get in this particular representation? 12 is represented as 1 and 23 is represented as 1. So 1 and 1 becomes 1. So the output you get x as 1. But this type of operation cannot be applied on this operation, means this line. Why? Because these are bitwise operators. That means the AND operation is exactly applied on the bit level of this 12 and 23. So there are two numbers. We need to see how these numbers get represented in your memory. Then we will apply the AND operation on this 12 and 23. So let us understand properly how this particular line gets executed in your computer. So to understand that, first of all, we need to understand how to represent numbers in your computer system. That is your 2's complement representation. And I know all of you have watched that video, 2's complement representation, so that you can easily understand this one. Okay, so as I know how the 2's complement is represented, so let us continue the discussion. So if first of all, let us take the first number, that is your 12. How it will be represented in the memory? It will be represented in this form. Here you can assume that this is a 32-bit computer, means integer takes 32-bit. So there are 32, in a 32-bit representation we have to represent 12. We know that 12 in binary will be 1 1 0 0. Okay, this is the binary equivalent of 12. So when you want to represent it in your computer with 32-bit, then the LSB, that is your least significant bit. So this part is called actually the LSB, okay, and this is called the MSB, that is called the most significant bit. So it does not require to remember all these things, but you still understand that whenever we want to store 12 is equal to 1100, 12 is in binary is 1100. So I have to write 1100 over here, and the remaining bits, so out of this 32, how many bits are there? 28 bit. The remaining 28 bit will be represented with 000. Okay, so all these are 0 now. So 12 has been represented with this manner. Okay, this is positive 12. Similarly, you want to represent a 23 also. So 23 in binary is actually 10110. Okay, 10111. Okay, so this is the binary equivalent of 23, and it is also represented in 32-bit itself. Okay, so you have to write all the binary equivalent of 23 towards the LSB bits, and the remaining bits are filled with zeros. Okay, so after you perform the binary equivalent or the 32-bit representation of all these numbers, then what you will do, you will apply the AND operation. So this AND operation, actually this is not AND operation, this is your bitwise AND. So that means on the bit level itself, this AND operation would be performed. So now you can see, so if I'll perform the AND operation, 0 1 becomes 0 and 1 becomes 0. 0 and 1 becomes 0, 1 and 1 becomes 1, 1 0 becomes 0, 0 1 becomes 0, and the remaining bits are 0 now. So all these 0, 0 and 0 becomes 0. So I'll write all the zeros over here. Okay, now whatever we get, that is the answer of this x value. So what is the value of x now? So this is in decimal conversion. If you convert this binary number into decimal, so this is equivalent to your 4. Okay, I hope you understand how to convert a binary number to its decimal equivalent. So the decimal equivalent of this number is 4. So that's why this output of this program will be coming as 4. So that is your answer. Okay, let us modify this program again and check how actually the bitwise operator works for the modified example. So let's continue. So let's say what the same program I have written. In this program, what I have done, I just changed the 23 into minus 23. Now it is mandatory to remember how to represent a negative number in a 2's complement representation. Okay, so let us I know that you have already watched the 2's complement representation of numbers, but still if you don't watch that, even you have not watched that, you can easily understand in this example itself. So let us understand it. Suppose I want to represent minus 23 in 2's complement representation. So first of all, we need to take the positive value of this 23. So what is the positive number? That is a 23, something like this. Okay, positive 23. We know what is the binary equivalent of positive 23 in 32-bit representation. Remember, this is your 32-bit representation. Okay, so in 32-bit representation, I will represent 23 as 1 0 1 1 1, and the remaining bits are 0 because this is a positive number. And in 2's complement, we know that the last bit, or we can say the MSB bit, that is your MSB bit, will be used for your sign bit. Okay, so as this 23 is positive number, so the sign bit is now it is 0, but we want to represent it into minus 23. So what will happen? There will be 2's complement representation we will follow. So what is 2's complement representation? First of all, we will convert the given number into its ones complement. So let us understand what is ones complement. In ones complement, every bit which is represented over here will be altered. Means 1 becomes 0 and 0 becomes 1. So what we will get? We will get 1 1. This is 0 0, so 1 1. These all are 0, so all are 1. So this 1 becomes 0, this 0 becomes 1, this 1 becomes 0, this 1 becomes 0, and this 1 becomes 0. So what is it exactly? It is the ones complement of the given 23. That is a positive number. Okay, so after you find the positive, means ones complement of this number, then 2's complement says that you add 1 to the ones complement. So that means we will add 1 to this ones complement, whatever we get. Okay, so I hope you know how to add two number in binary. So let us add it. 1 plus 0 becomes 1. Then there are all other will be, there will be no addition is given. So I will directly write all these numbers. So 0 0 1 0 1 1 1 and something like this. So what exactly this number represents? This exactly represent the minus 23. Okay, where this bit, the last bit, you can see it is now 1, which is representing the sign bit. Okay, so now that you get the minus 23 value as this, now you need to represent 12 in 2's complement representation, but it is a positive number, so we can directly represent it something like this. We have already discussed this one in the previous slide itself. So after finding out the minus 23's representation and 12's representation, now what we will perform? We will perform the AND operation. So let us perform the AND operation. So 1 0 becomes 0, 0 0 becomes 0, 0 1 becomes 0. So whenever there is 1 1, then only the output becomes 1. So this will be 1. 0 0 becomes 0. So these are all ones, these are all zeros. That means what we will get? Everything will be 0. Okay, so now whatever we get over here, that is actually the output of this x. So what we get here? 1 2 4 8. So that means we get 8 actually. So that's why the answer of this program will be 8. So whenever you will print the value of x, so x becomes 8. Now that you understand this one also, so let us modify this program again by taking both the number as a negative number, so that it will be more clearer to you and you can recall the 2's complement representation of any negative numbers. So what I have modified? I have modified the same line and I have represented 12 as minus 12 and 23 as minus 23. So let us represent these negative numbers first, then we will perform the AND operation. So how to represent negative number? First of all, we will take the positive equivalent of the negative number, that is 12. That is, so minus 12 is 12. Now 12 in 32-bit will be represented something like this: 1 1 0 0. The remaining bits become 0, and we know that this particular bit represents your sign bit. Okay, so after getting the binary equivalent of positive 12, what we will do? We will represent the ones complement. So we will make its ones complement. So this is your ones complement. So ones complement means alternating the value from 0 to 1 and 1 to 0. So 0 becomes 1, 0 becomes 1, 1 becomes 0, 1 becomes 0. The remaining bits are 0, so all these are 1. Now after finding out ones complement, so for 2's complement says that you have to add 1 to it. So we have to add 1. So we know that addition. So whenever 1 plus 1 becomes added, you get 1 0. So out of this 1 0, you keep 0 here. Okay, you keep 0 here and take carry as to the next bit. So it is something like this. So you'll keep 0 here, carry comes 1. Then 1 plus 1 is again 1 0. So you keep 0 here and carry as 1. 1 plus 0 becomes 1. Then there will be no number to be added. So all these bits has to be represented over here. So I have represented all these numbers. Now what is this? this is actually the minus 12. Okay, representation of minus 12 in the memory. Now that you understand how to find minus 12, and we have already calculated the minus 23 in the previous slide, so let us write it for minus 23. So this is minus 23, and you can see this bit and this bit represents what? This represents your sign bit. Okay, now you have to perform what? You have to perform the AND operation over here. So how to perform the AND operation? We know that whenever the both the bits are 1, then only the output becomes 1. So let us perform the AND operation here again. So 1 0 becomes 0, 0 0 becomes 0, 1 0 becomes 0, 0 1 becomes 0, 1 0 becomes 0, and the remaining bits are 1. So I can directly represent by the help of 1 on all the places. Okay, so what does you get? You get a negative number here. How do you know that this is a negative number? Because due to this 1 over here. So as the sign bit is 1, that's why this is a negative number. But how could you know that this is whose negative numbers representation is? So whomsoever negative representation is this, that is the output of this program. So let us find out whose negative number representation is this number. Okay, so how to do that? So to find out the negative whose number is this, so first of all you have to write that number. Okay, then you perform the ones complement again. So this is your ones complement. We found out the ones complement of this output. So whatever output you get in the previous slide, I just converted into ones complement. After finding out the ones complement, we have to add 1 to it. So after adding the 1, you can see 1 plus 1 becomes 1 0. So put 0 here, carry 1. Then again 1 plus 1 becomes 1 0, put 0, carry 1. 1 plus 1 becomes 1 0, put 0, carry 1. 1 plus 1 becomes 1 0, put 0, carry 1. Again 1 plus 1 becomes 1 0, put 0, carry 1. Okay, now 1 plus 0 becomes 1, and the remaining bits are what? Remaining bits are 0. So I'll put all the zeros over here. Now whatever value you will get, you just convert it into decimal equivalent. So what is the decimal equivalent of this number? 1 2 4 8 16 32. So this is the decimal equivalent is 32. So but it is a negative number, as I have already told you, because it is a sign bit. So that is the this is the representation of what? This is representation of minus 32. So what should be the answer of this particular program? You will get the answer as minus 32. So this is how you will perform the AND operation. I hope you understand the entire thing that I have explained particularly. Now I am giving you a question. So the question is, I am taking minus 12 and plus 23. So try to solve this problem in your computer and see what is the output, and analyze how the outputs are coming. So you can also solve for bitwise of OR and XOR operators. I have given some questions over here by using your bitwise operators, that is pipe operator has been written over here. I am taking the same example, that is 12 and 23, and I know you can easily find out this value, because all these number, how to convert 12 and how to convert 23 into binary number, you all know. So after converting this, you have to perform the OR operation in this case. In this case also you will perform OR operation, but in this case you will perform XOR, and in this case also you will perform XOR. So after performing according to the truth table, you have to perform the operations and check what should be the output of this program, as well as check why the outputs are coming like that. So that's all for the today's class. Thanks for listening. Goodbye.